Hello everyone, welcome to Gate Pass, and today in this video I am going to take 4 problems which appeared in Gate 2019. So first we will start with problem number 25. It's a very, the problem statement is very big, and believe me, the solution is 1/4 of the problem statement. So let's first understand the problem. Okay, so it says that you have a sealed rigid bottle which contains water in which CO2 is dissolved, okay, and the pressure inside this bottle is 10 bar. The gas phase you are asked to assume that it's pure carbon dioxide and assume it as an ideal gas, and the liquid phase, that is it has CO2 which is dissolved in H2O, and you have to assume it as an ideal solution. Now they have said that the temperature is ambient temperature. We will take it as constant. Okay. The pressure given is 10 bar, and the Henry's constant at this temperature and pressure, that is also given, 1000 bars. Now you have to find out the mole fraction of CO2 in the liquid phase. Okay. So let's first understand why they have given you that your gas phase is an ideal gas and your liquid phase is an ideal solution, because it comes out in the derivation of your Henry's law which you use. Okay, so let's quickly see. You have already seen what is ideal gas mixture model. You have already seen what is ideal solution model in 2022 Gate solution. Okay, if you have not seen it, you can go back and see it over there. So in this case, I have written both the ideal gas mixture model, that is in terms of your Gibbs free energy of species I when it exists as ideal gas, plus RT ln Yi. Yi is the mole fractions in the vapor phase. Okay, over here Gi, it is the Gibbs free energy of the species I at system temperature, pressure, and in its physical state, which is its real physical state at that solution temperature and pressure. Mind it that the quantities which I put in capital letters, these I am using as molar quantities. Okay, so this is Gibbs free energy per mole. Fine. So this is your ideal gas mixture model and ideal solution model. Okay, now if you have two phases which are in equilibrium, one we have to assume as ideal gas and the other I have to assume as a ideal solution. Okay, then if they are in equilibrium, as is the case in this problem, then your chemical potential of any species I in the vapor phase should be equal to the chemical potential of species I in the ideal solution, right? So we can equate these two. Okay, but before that, let's do one thing. Let's simplify this term over here further, or elaborate it further. So this is my Gibbs free energy of species I when it exists as an ideal gas. Let's, for a pure ideal gas at constant temperature, okay, and for constant number of moles, let's say, we write this equation. You have all seen that dG, that is equal to VdP minus SdT. Okay, since we are keeping temperature constant, so I am neglecting that term. So I am writing it as Vig dP. Now this exists as an ideal gas, so I am using ideal gas law to write V in terms of T and P. Or equally well, I can write dP by T as TL and P. Now if I integrate this equation in order to get this term over here, what I get is RT ln P plus some constant which is a function of temperature. Okay. Now I am going to put this in my ideal gas mixture model. So what I get is basically mu I Ig, that is equal to the constant of integration plus RT ln Yi plus RT ln P. So I can combine these two terms and write RT ln Yi into P. Okay. Now I am going to equate the chemical potentials in the vapor phase and the liquid phase. Okay. So that will be my constant of integration plus RT ln Yip, that is equal to Gi plus RT ln Xi. Okay. Now rearranging this equation, what I get is that, let's combine these ln terms. So what I get is Yi into P upon Xi, that is equal to exponent of, okay, yip minus xi, so I will take it over there, gi minus that constant of integration, which is a function of temperature, divided by RT. So in this case, gi is a function of temperature and pressure. This is a function of temperature, okay. So at any given temperature and pressure at which your equilibrium exists, okay, this term here, it can be taken as a constant, and let's call this as Hi or Henry's constant, okay. Now I can write my Henry's laws as Yi into P, that is equal to Xi into Hi, okay. So this is your Henry's law. Now let's say I have a binary solution. So I am denoting my solvent as component 1 and my solute as component 2, okay. I will take some more space. Now you have understood this. So now let's elaborate on this equation now, okay. So you can write it for both the components because I have derived it in a general way. So I can write for my solute, I can write Y2P, that is equal to X2H2, okay. Now let's say that I have a very dilute solution in this case of CO2, okay. That means my X1 tends to 1 and my X2 tends to 0, okay. So when I am writing for component 2, what I am saying is that my X2 tends to 0. In that case, what it gives is Y2P is nothing but your partial pressure, let's say P2, that is equal to X2H2, okay. Now this is a constant which you can obtain experimentally. If you know the partial pressure, you can calculate the mole fraction of your solute, okay, in the solution, fine. So that is what, it is a very simple problem over here, and we are going to use this equation. I will get back to another case in which, okay, your X1 tends to 1. Now I am going to write it for component 1. How do I write? Y1P, that is equal to X1H1, okay. When X1 tends to 1, what happens? This is nothing but your partial pressure, okay. When X1 tends to 1, what happens is that your partial pressure approaches your saturation pressure, right? So in that case, what happens is your H1 will approach the value of saturation pressure, okay. If I put this value over here, what I get is YIP, that is equal to X1 PSAT, and it is nothing but your Raoult's law, okay. So what you do is, when you have a problem in which X2 approaches 0, you use your Henry's equation. When you have a problem in which you say that your X1 approaches 1, then you use your Raoult's law. Raoult's law can also be used if you have a mixture of components which are homologous, like part of homologous series, like say xylene, benzene, toluene. So which are chemically identical. If you mix them, then you can apply Raoult's law in any for any composition, okay. Otherwise, you apply when your X1 tends to 1, okay. So one more thing is that this is applicable for your ideal solution, but if your solution deviates from ideal behavior, then you introduce a component, let's say gamma 1 x1 psat, okay, where this is your activity coefficient which we have seen before, and this takes care of your non-ideal behavior. It should be by 1, yeah, we are writing for component 1. So this is now your modified Raoult's law, okay. So what you see is that in this problem statement, they have given you all the assumptions which they have used to derive basically your Henry's law, and then I have gone through the cases where you have to use Henry's law, or you have to use your Raoult's law or your modified Raoult's law, okay. So now we will see that this problem is really very simple, because in this case I am going to use my Henry's law. Now your partial pressure P2, which you don't know, but what they have said is that your vapor phase is essentially 100% CO2, so the total pressure will be equal to your partial pressure. So in this case I can take P2 as 10. Your Henry's constant is given as 1000. You have to find your X2. So then your X2 comes out to be equal to 0.01. That is the answer which is given in the key. So next we will take a problem which is based on your application of modified Raoult's law. So the second problem is question number 5, in which a binary non-ideal mixture is given, and it is said that it shows a minimum boiling, it forms a minimum boiling azeotrope. Okay, now it says which one of this is correct about the activity coefficient. Okay, so let's first understand the system on Txy and Pxy plot. Okay, so when it says that it shows a minimum boiling azeotrope, then you have a minimum in the boiling point over here, as you see. Okay, that will correspond to a maximum in the pressure when you plot it on a Pxy plot. Okay, so what you see over here is that if you have two components, okay, I have plotted PA versus XA and PB versus XA. Okay, in this case what is happening is that these dotted lines, these are my ideal lines. Okay, so these I have obtained from Raoult's law. So both the component, it shows a positive deviation from ideal behavior. Okay, so in this case, that's why this plot is above the ideal solution line, and this plot is also above the ideal solution line. Okay, so both these partial pressures, they are showing me a positive deviation from ideality. Now if I plot a total pressure versus XA curve, which is nothing but the addition of these two curves, it also from ideality it shows a positive deviation. Okay, so for this case what I have to use is now my modified Raoult's law. Okay, so I am writing it as gamma A XA into PSAT. Fine, but your Raoult's law, that is for the ideal behavior, it is XA PSAT. Okay, now what you see over here is that for non-ideal you have like whatever you have estimated XA gamma A PSAT, that is greater than your XA PSAT, which is for the ideal solution. Okay, so this can be greater than this only when your gamma A is greater than 1. Okay, similar is the case, it can be greater only when your gamma B is greater than 1. Fine, so out of these options this one is correct. Now if the question had come in a different way, that it shows a maximum in boiling point, so the azeotrope is a maximum boiling azeotrope. Okay, in that case what you will have is like a maximum on the Txy plot, that will correspond to a minimum in the Pxy plot, because now your these actual curves, they will lie below the because it is now showing a negative deviation, so it will lie below this ideal solution curve. Okay, the dotted line. In that case what will happen is that the actual partial pressure which you are calculating is less than the ideal, so it can happen only when your gamma A and gamma B is less than 1. Okay, so the reverse will be true for that case when you have a maximum boiling azeotrope. In this case it's a minimum boiling azeotrope, and we have found that your gamma A should be greater than 1 and gamma B should be greater than 1. Okay, so the third problem is question number 4, which appeared in GATE 2019. It says that a single component system where your vapor and liquid phase is in equilibrium, and it is asking that when a chemical, physical and thermal equilibrium is maintained, then which one of this will be true. Okay, so your U is your specific internal energy, your H is your specific enthalpy, S is specific entropy, and G is your specific Gibbs free energy. We all have seen previously that yes, your Gibbs free energy, molar Gibbs free energy is the same in gas phase and the liquid phase when both the phases are in equilibrium. Let's understand why they are same. Okay, because this is you have quite often seen, but let's go and understand why your molar Gibbs free energy in the two phases are same. Okay, so for to understand that, I have taken a liquid, saturated liquid in a piston cylinder arrangement. Okay, now let's supply Q reversible amount of heat. So in a reversible process, I am supplying Q amount of heat to it at constant temperature and pressure, and let's say that now it gets converted into saturated vapor. Okay, so 1 mole of saturated liquid, I am supplying heat and converting it to saturated vapor, right? Now from Clausius equality, I can write that the Q reversible which is supplied, that is equal to T times Sg minus Sf. Okay, now we also know that because this is a constant pressure process, when I apply it to first law, then your heat supplied, that is equal to the change in the specific enthalpy. Okay, Since I am applying, see the heat supplied is same, so I can equate these two. So I can write T times Sg minus Sf, that is equal to Hg minus Hf. Or if I rearrange this equation, what I get is that Hg minus T Sg, that is equal to Hf minus T Sf. Or you know that H minus Ts, that is nothing but your G. Okay, so I can write G, that is equal to molar Gibbs free energy in the gas phase, that is equal to your molar Gibbs free energy in the liquid phase. So when you have two phases which are in equilibrium, then your molar Gibbs free energy in both the phases comes out to be same. Okay, this is question number 38, which appeared in GATE 2019. Here they have given you the molar volume of a mixture at constant temperature and pressure as a function of mole fraction. So it's a binary solution consisting of component A and B, and they have given this function. Now they have asked you to calculate the change in the molar volume when you mix XA and XB. Okay, and your XA is 0.5. So that's what they have asked you. They have asked you to calculate the change in the molar volume upon mixing. Fine. So let's see. First of all, it's very straightforward. You can find out the molar volume of this solution because this is the function which gives you. So I can calculate my molar volume when XA is equal to 0.5. So I put XA equal to 0.5 and XB equal to 0.5 and calculate my molar volume for this solution, and it comes out to be 26. Okay. So your units are given as meter cube per mole. Now you all know that for ideal solution, the change in the property, change in the volume upon mixing, that is given as V minus summation Xi Vi. Okay, where your Vi is the volume of that species I when it is in the for the pure species I. Okay. For an ideal solution, if it formed an ideal solution, then it would have been 0. But now you have certain change in that property, that is what we are denoting by delta V mix. Okay. So now you have evaluated this at 0.5, you have to evaluate this. Okay. But VIs are not given. For that again we go back to this equation. If I put XB equal to 0 and XA equal to 1, then I can evaluate my VA, okay, from the same equation, which comes out to be 30 meter cube per mole. Similarly, I am going to evaluate my VB from the same equation by putting XB equal to 1 and XA equal to 0. So it comes out to be 20 meter cube per mole. Okay. Then my summation Xi Vi, that will be equal to 0.5 into 30 plus 0.5 into 20, that will be equal to 25 meter cube per mole. Okay. Then your volume change of mixing, delta V mix, at x equal to 0.5, that will be equal to V, which you have calculated, 26 minus 25, that is equal to 1 meter cube per mole. So it's a very simple problem. Okay, that is the answer which is given in the key. So you have to find your change in the volume upon mixing, and only one equation is given. So you can calculate everything from this equation. So that was your problem. So there are two more problems which are remaining, which appeared in GATE 2019, which we will take in the next video. So I hope you understood, and if you like this video, please don't forget to leave comments, because it will motivate me to make more such videos, and please subscribe to my channel. Thanks for watching.